Hi, everybody. I am, had so many buttons on my screen, I couldn't figure out where the play button was. But I am going to talk tonight about advanced features of Scala 3. And there's not too much I can say in 30 minutes. So I just wanted to kind of give you a few views of various features that are probably not something you'll run into that often. They're the kind of things that people use when they're when they're designing a library or a framework, but you don't tend to use them every day except through libraries and frameworks. So anyway, I'll actually, it's kind of a grab bag of things. So the first thing I want to talk about was opaque types, which isn't really advanced, I think, but I wanted to start with it to warm you up. This is something new in Scala 3 that is trying to address an deficiency of any vowels, and any vowels were trying to address an deficiency of any ref. So any vowels look like this, and this works in Scala 2 or Scala 3. This still works in Scala 3, and basically you just make a class, looks like a regular class, but you say extends any vowel. Except it has some special rules that you have to follow, and one of them is that this class has to wrap one other class. So here, class text wraps a string. It has to have one and only one class parameter there. You can have other implicit parameters if you want. But the efficiency that this will do is that at runtime, when possible, the compiler will actually just pass around strings instead of texts. And any methods you add to this class will be optimized into like an extension method, essentially, where you pass the string in first, and then it has the other parameters. So it's an efficiency thing. The feature of this guy, though, is it will box when need be. Like whenever a primitive type would box, this would box, which and boxing means usually it means going from the stack to the heap. But in this case, like since the string, this is the JVM, strings are always on the heap already, so it'll make another object on the heap called text, instance of class text, that points to the string. So if you like, for example, make a list of text, it'll make if there's 1,000 texts objects in that list, it'll have 1,000 text instances on the heap. But if you just pass a text to a method, it will actually just pass a string. So anyway, it has another feature that, for example, you can implement an interface. And so whenever you use it through that interface, it boxes it. So there's all kinds of times when it boxes. So what was desired for a long time was a way to not ever box. And that's called an opaque type. And so this works in Scala 3 only. And an opaque type is sort of built on type aliases, which existed already. A type alias is you just say type Fred equals Ginger, and now the name Fred means Ginger, means the same exact thing. And if you put opaque in front of it in Scala 3, what that means is that inside the template that you're in, so I'm in object example, that's the template. Example is either an object, a trait, or a class. It's just the same thing. It's just a regular old type alias. They just are two names for the same exact thing. Logarithm just means double. But outside, a logarithm is opaque in the sense of you can't see through it to double. You don't know it's a double. And so that's basically kind of like, if you look back here, text at runtime is really a string most of the time, but you don't know it's a string. So it's that kind of concept. Logarithm is really a double at runtime, but you don't know it's a double. So because they're two different things, you're going to need to offer some ways when you make one of these for your users to, given a double, get back a logarithm. So I've got two factory methods here. And what you can notice, because this is inside the template, like this first apply factory method, it actually, the right-hand side, the body math.logd, that's going to produce a double. And I just say it's a logarithm because it's a type alias here. It's just a regular old type alias. Because I'm inside the template object example. So those are my factory methods. And then the other thing, I've been back up here to my any val, is I can add methods right there like a regular class, and you can invoke those methods on an instance of text, and it's optimized away. They don't box if they don't need to. And so I can't do that here because there is no class. So I'll never get an instance of class logarithm because there isn't one. It's just a type name of a type. So what I need to do is use extension methods. So these are Scala 3 extension methods. And so this is basically the pattern of making an opaque type. I say inside sub template, I say opaque type, something equals something else. Then I'm going to have some factory methods. So I can go from the underlying type to the opaque type. And then I'll probably have some extensive methods to define a public API of it. So, so that's, one use case for these, for both of these things, both antivals and opaque types, is tiny types. So if you have like a bunch of strings, but they kind of mean different things, like one's an address, one's a street, one's a city, one's a state, then you could actually make these little types like class state that has an underlying string extends anyval. And it sort of gives you type checking for not much cost at runtime, because there is a cost to every class that's instantiated on the heap. So that's the cost we're trying to avoid with these two features. So that's one use case. Another one that's really nice is you make little hierarchies of these things. So for example, in Scholastic anyvals, we have this package called anyvals. We have a bunch of anyvals for different kinds of, well, usually numeric, but they can be other things, but they're narrow things. Like right here, text will take any kind of string, but we have an anyval called posint that has an underlying int, but it promises that it will always be a positive integer. And then we have one called posint that it takes an underlying int, promises that it will always be positive or 0. And so if you think about it, if I need a positive or 0 int and I have a pos int in hand, that should work. It's really a subtype because both of them are underlying are ints, and any posint is a valid posint, right? So that's like a subtype. And the way we implemented that in Scholastic was we just have implicit conversions in Scala 2 from posint to posint. It makes it kind of a subtype. And if you think about, like, there's one way to think of I can pass a subtype to a supertype where a supertype is expected. There's like an implicit conversion from subtype to supertype when I do that. So we hard code all those, but they're not transitive. I have to have every single implicit conversion explicitly done. In opaque types, you can actually put a little less than colon something. So I could say opaque type posint less than colon posint equals int, if I wanted to do that. So that's a nice way to make little hierarchies of these things. So that's basically opaque types. The only other thing I wanted to mention is this is still around. It does have other features. So I mean, different feature set. Maybe it's useful to stand on its own, but it's kind of almost two different ways to do the same thing. There is a project in Scala or in Java called Valhalla, which is to put value types into the JVM. And so maybe this will get sort of shoehorned into that use case if and when that comes into the JVM. But anyway, so that's the status of that. So that's one. And I just said, this is kind of a grab bag. So I'm going to kind of go through these quickly, but you can ask questions after. So type lambdas were added to Scala 3 because they were wanted by the community for a really long time. And the community wanted so bad that they came up with a very ugly way to do it in Scala, which turned out to be unsound from the type system point of view. So that got ejected. So they can't do that anymore. So they kind of needed this to replace it. But also, a lot of people use the compiler plugin to get this thing. But anyway, it looks like this. And I made it purple for two reasons. One, that's the color I color type, so I'm syntax highlighting. The others is a little less scary looking. But you can just think of this as another lambda, but it's a lambda at the type level. So, and it looks like, these are all types. K and V are types, but this is really like oh God, I don't want to say it that way. That makes it sound worse, but it's just a lambda. Like in lambda calculus, like we have these function literals in Scala source code that are terms. This is like that, but at the type level. And so its parameters are in square brackets because those are types, not terms. If they're in parentheses, that means they're values or terms that you have to pass in. Here I have to pass in types. So that means this thing's going to be evaluated at compile time. And so if I pass in like string for key for K and int for V to evaluate that, it just substitutes. And what I get back is map string comma int. So that's all it is. And it's used to, for example, to like if you want to make a functor of an either, well, that actually got solved a different way. But anyway, it was used to sort of in type level when you're trying to change the number of usually it's used to change the number of holes in a type. Like this is you could think of this as a type that has two holes in it. I got to plug in two types and I get back one type. So anyway, that's called a type lambda. And the one thing that's a little interesting design choice that I wanted to point out is that in Scala, type constructors, and you kind of think of this as a way to construct a type. I pass two types in, I get one back, have variants, right? Because you're gonna have subtypes. So the V over here in map, if you go look at how map is defined, the V has got a plus sign next to it. That means it's covariant. And in these type lambdas in Scala 3, you cannot put a plus sign next to the V over on the left-hand side. You can't actually do that. It will always be inferred. It says because V is a covariant in the body, then V is going to be covariant in the parameter, even though it's not, there's no plus sign there. So anyway, that's how that's done in Scala 3. And the other thing I was just going to say about this is, people wanted pure functional programming. Like in Scala, you can do anything anywhere. So our lambdas can have side effects. This one is pure. So it actually is like lambda calculus, like it was meant to be. It doesn't have any side effects when you evaluate these things. Okay, so that's that. So something that looks a little bit similar is polymorphic function types, which I think will be used a lot more rarely. But it's two things. It was, there's use cases for these and people ask for it, but it also removes something that is different between methods and function values. I think there's a kind of simplicity you can get when you don't have special cases. And a method, you should be able to think of that as like a val. Instead of a def, it's a val that refers to sorry, I'm at my friend's house and this is his phone answering machine. So anyway, a val that sort of refers to a lambda. I mean, that's another way to think of it. I'm going to say that again. So a def, which is a method in Scala, is really conceptually no different than a val that is referring to a lambda. It's you apply the lambda, you pass parameters into it, and you get the result, right? That's what a def does. It's just like syntax sugar for that, except it has extra features. There's things you can do with defs you can't do with vals pointing to lambdas. For example, you can't do var args. When you 8-expand a def that takes var args, it actually gives you a seek, right? There's no way to write that by hand. There's actually a weird way to get a var args lambda, but that's also not regular. You can't actually write a literal with var args as a lambda. You can't do default parameter values either. You can do that in a method, but you can't do it in a lambda. And the thing in Scala 2, another thing you can't do in Scala 2 is you can't have a polymorphic function value, but you can have a polymorphic method. So this rev method here takes a type parameter A, and then the parameter that it takes, the in parens, that's a value parameter, is a list of whatever that type A is. So if you say A is string, if I pass string in there, then I have to pass a list of string and I'll get back a list of string. If you pass int there, then I have to pass a list of int and I'll get back a list of int, right? That's just called parametric polymorphism. And we've been able to do that for methods for a long time. But if we were to 8-expand that, you can 8-expand such a method in Scala 2, which means turn it into wrap it in a function value. It will infer and pick a type for A. So I'll get a function value in Scala 2 from list of int to list of int, or one from list of string to list of string, depending upon what the context is. And that's the exact same default in Scala 3. But what's added in Scala 3 is I can actually write that same kind of thing. And it looks like this, the second line there, that's called fun. It is got in square brackets an A. That means that you're first going to have to pass in to this lambda a type, sort of, you can think of it that way, and then it will produce, the thing to the right of that arrow, which is a function value from list of A to list of A, whatever that A was. So that's the purple thing after val fun colon is the polymorphic function type. And so it sort of means the same thing as def rev up there. Given an A, then it's going to take a list of A and give you back a list of A. That's the type that means that. And then the literal, the function literal, or the lambda is the part on the next line here, square brackets A rocket, and then you have a regular function literal that uses that A. So you always have to write that out explicitly. Otherwise, it will assume it's going to eagerly decide what A is. So that's a polymorphic method. And I think what's going to be, function type. And what's a little bit confusing is we got a lot of different kinds of arrows now. Not arrows, but like this square bracket A, regular rocket, that if you see that, that's going to mean that either to the right-hand side is a type, which is a function type, that's the purple one on top, or it's going to be a lambda, which is the value. And if you compare that to this guy, what's different is he's got a double arrowhead. So the double arrowhead means type lambda. I've got some types in square brackets, and then a double arrowhead, I've got a type lambda. What's over to the right-hand side doesn't have to be a function type. And down here, I have the single arrowhead, and what's to the right of it's got to be a function type because that's a polymorphic function type and value. Okay, so that's one. So there may be questions about that, but we can talk about that. So I want to talk next about match types, which also got added in Scala 3. And this was because people wanted this. They wanted to be able to compute a type from a type, essentially. And there is a way to do that in Scala 2, which is to use implicits to abuse implicit lookup. And so everybody did it, including me, because that's how you did it in Scala 2. And so what Scala 3 added is this thing. It's called a match type. And so there's that type keyword again. And I always thought it was kind of funny that sometimes the type keyword have square brackets like that, because this looks more like a method, actually. It is, I think, a good way to think about this, like the difference between a type lambda and a type match type, is that a lambda is like a type lambda is a lambda, and a match type is the method. It's, the name of this method is, it all runs at compile time. It's a type level method. Its name is elim. It takes one parameter x, which is a type, and it returns a type. And, basically when you call elim x, you just replace that, or when you mention it as a type, it will just replace it with one of these result types here. So it's just, it works like a match at the value level, except I'm matching on a type. So I say x match, where here x is a type at compile time. If it was a string at compile time, then the result of this match type is char. If it was an array, then it's going to, the t is the element type of that array. It's going to pop out and be available on the right-hand side of that rocket. And you get that as your element type. So if it's an array of int, then the result of this is going to be int. Otherwise, if it's an iterable, again, the t is going to pop out. So if it's an iterable string, then your result will be string. And if it's not one of those, then that's a match error, right? But this is a compile time. This is always run at compile time, so it gives you a compiler error. So that's a match type. And so I think just one way to think about this is, you can think about this as like the method, the type level method, to the type lambda's type level lambda. That's really what they do, the same thing. Given types being passed in, you get a type as a result, and it just substitutes. Okay, so that's that. And just rolling right along, I'll give you another one, dependent function types. So I just, as an aside, one of the original tasks for Scala 3 was to simplify the type system by replacing 3 pieces of it with exact replicas that were defined in terms of other existing pieces. So an example of that is in the Scala 2 language spec, there's the description of type parameters and a description of type members, a definition of them. They just define them, specify them, and they're 2 different things. So in Scala 3, there's the description of type members, but then type parameters are now defined in terms of, they're like syntax sugar for type members. So that you define this in terms of, here's how you rewrite this to type members. So really you just have one feature. So that actually was, I thought, a big accomplishment. It had to do with like the soundness proof follows. The soundness proof just talks about type members. But then a whole bunch of other things got added, like you've just seen several of them, right? So dependent function types is another one. And this one, again, there was reasons for wanting it. I think a big one was just consistency or regularity. That, it's another case where in Scala 2, a method can have some feature, but a lambda cannot. So in Scala 3, the lambda can now have this feature. And the feature is that a method's result type can depend on its parameter, a type member of its parameter type. So here I've got a trait entry that has one type key. That's an abstract type. So to have an instance of entry, I have to have a class that extends entry and fills in some type for key. So let's say type key equals string. Class string entry, type key equals string, or a class int entry, type key equals int. So I have some like concrete subclass. And what this extract key method, the dependent method, does is at every call site, there's some subclass that's being passed in. And I need to know the specific subclass so that I can tell at that call site what e.key means. So if I'm passing in a string entry somewhere, then at that call site, e.key means string. And that type checks. So if I'm passing an int entry somewhere, then e.key at that call site means int. So that's how that works. That's not used that often, but it's actually quite useful. It's used in libraries. dependent, path dependent types. But before, I don't know if you got an error when you try to 8 expand something like this, but you couldn't actually make a lambda like that. But now you can. So that looks like the second line there, val extractor. And then the purple thing is the type. I make types purple, and except I forgot to make that one type purple. But anyway, this type is purple, and it is a lambda type or a function type that takes an entry and returns the key type inside that entry. There's a path dependent type there. So that's now possible in Scala 3 also. It's called a that dependent function type. Sorry, okay, one too many types of types, I think. This is not a Scala 3 marketing. This is all like these things are in there. You'll rarely see them, but it's kind of good to know that they're there because you might see them now and then. So I wanted to finish with talking about metaprogramming because I think that's a really big thing that got matured and finalized in Scala 3. It's something that was experimental in Scala 2, and everybody used it because it was so useful. So we all had to rewrite our libraries to use this stuff. And where it really, I think, is about is that I think ever since I've been programming, I often would feel the tug to automate writing source code. So I had one summer job where I was given all summer to finish this guy's work where he had written by hand all these really long lines of ones and zeros to test some hardware. And that was going to be my summer job. And I thought, well, this is very tedious and you could automate it. So I wrote a C program to write that code. So it's a program that writes a program. And so basically after a week, I said, okay, what's next? So that was one. And it just is like, we're programmers and a lot of what we do is repetitive. So we tend to want to write programs to do that. And we had like, at one point I decided that none of the Java web frameworks, this is a big mistake. One of the Java web frameworks were good enough. So I wrote my own and we're still using it. We're still stuck with it. And it uses a lot of code generation because there was a lot of repetition in these web frameworks. And that's what I thought could be done better. And it works really nicely, actually. But what it does is generate Java source code. And then we use that Java source code. And it generates a class and we extend it, that kind of thing. We do things by hand. But there's a lot of downsides to it, like when you go to your IDE and look at the by hand written class that extends the generator one, well, it hasn't been generated yet, so it doesn't see it, right? So the IDE it has clunky IDE support, and there's a bunch of other issues. So one time I remember mentioning that I like to do this code gen thing on the early days of the Scala mailing list, and I got a huge backlash that complaining about that, all the problems with code generation, which are real. But what one person said is that if you're feeling the need to do code generation, then there's something missing from your language. And I think what all this metaprogramming stuff is about is trying to bring that kind of thing into the language where I can write programs that write programs, but it's all part of the language so that you'll get good IDE support and all those other issues are not there, right? So so there's a whole bunch of things to it. I'm not going to show you everything, but what I'm going to start with is inline. Inline is just, it's a new keyword. There's an at inline in Scala 2, which is different. That's like a hint. But this is like inline. And inline without an at sign means definitely inline. And inline just means, if I have an inline def, like here I have an inline def log, instead of when I invoke log, pushing a stack frame, creating a new stack frame on the stack and pushing, the parameters there, and then jumping to the log method, and it executes using the stack frame, and it can use it for its local variables, and it puts its result there, and then it, returns. It takes the code of the body of log, and it just sticks it right. It just replaces where you call log. It just replaces it right there, and that's what inline means. It just do it inline. It's the same thing the JIT compiler does to make your program faster. If you're calling a method over and over really fast and you don't want to have it decides it would be faster to just take the body of that method and stick it right there. So that's why the hotspot of your code with the JIT, hotspot JIT compiler, a lot of stuff just gets flat. There's no method calls because it inlines everything that is needed to be inline for performance. So it's a space-time trade-off. So anyway, what this is going to do when you call log is it's going to, because it's inline, is it's going to actually put that body there, except there's a little bit more to this story because there's logging up there at the top is inline. And we have a little if, an if then else in the inline def that it switches on that logging value. So because it's an inline, it will actually decide, it will either do the then side or the else side every time it's used. It won't do both of them. It won't do this if at runtime, it will do the if at compile time. So for example, if I have this factorial method where I say, hey, log that I'm calling factorial, and here's the body of factorial, it's in the curly braces. That's the op, by the way, if you look up here, op, that is a biname to some type t, and then it returns t. So if logging is false at compile time, then you're just going to get the op. You see, let's go hop down to the else. It just gives you whatever the op was. But what it's going to do is it's going to take the code that you pass in these curly braces and just stick it right there. So here, if logging is false, you look at the bottom of the screen, my factorial method turns into this at compile time. Essentially, that's what I get. But if logging is true, then it's going to go to the other branch and it's going to actually stick a log message before and after, essentially. And the val result equals op, it kind of remembers what the result was and it returns it at the end after the log message goes out, the second log message. So you can see that here, this is if logging was set to true. Now it just replaces that with all that logging junk I get, and result equals the body that was passed as op. So that's how inline works. It really is basically well named. It's inlines. That's what it does. And then there's another feature called transparent inline, which is what happened to white box macro. Basically, what happened to macros that can compute types. That was useful, but very dangerous and very hard to understand. And just we decided it was too, well. So this is a more disciplined way to do that. So what works, the way this works is, so I have an example here. There's an animal and a bear that extends animal, and the bear class has a roar method, but the animal class does not. So I made a transparent inline choose method. So this is an inline method. It's going to do the substitution thing. But what's different about transparent is now the result type of this method, which is animal. It's set as animal. It at compile time may be narrowed to something that is a subtype of animal. So it will always be an animal. But like normally when you say it returns an animal, then at runtime it can return an animal or a bear or a cat or whatever. But what transparent inline means is that at compile time, we may decide it returns type bear. And it's just inferred. So if you look in, like the body here just says, if C is true, then I'm going to return a new animal. That means the result type is going to be the result of the substitution. The code that's substituted is exactly animal. On the other side, and that's like val A equals choose true, basically. That's the true side. And the static type of A is animal. If C is false, then it's going to say new bear. But because bear is a subtype of animal, the actual static type of that substitution, when you do the inline substitution, is going to be bear, not animal. And so val B equals choose false, the type of B is bear. So that's what's new. And they can also be recursive, and you can do all kinds of stuff. And if you look at a.roar, of course, that's a compiler error because there's no roar in animal, but b.roar works fine. So that's called transparent inline. And the other thing, the last thing I was going to show you, this is like one little slide for this massive subject, but it's quotes and splices. And I think a really useful way to think of this is it's like string interpolation, but for source code. So there's this thing called an expression, EXPR, which is like an AST of source code, an abstract syntax tree of source code. You can think of it. And that's like, if I'm writing a program that writes programs, this is my data structure. I'm going to manipulate these trees called EXPRs, expressions. And the quote is like double quotes on a string. I'm saying this is string, but here the quote is it's code, it's an expression. That's the data structure for it. And then if I have a string interpolator, say $name, like say hello, comma, $name in my string interpolated string, it's going to take that string or call toString on that guy and then splice it right in there. So what happens here is message expr is an expression. It's an AST. It sort of evaluates it. Excuse me. It just puts hello there. Oh man. Funny thing is my 30 minutes just finished. My 30 minutes just finished right when my voice ended. But let me finish one more minute. So what happens here with the $sign is just like plugging in when you do string interpolation, except instead of plugging in a string, you're evaluating the expression, you're plugging that in. So what you'll get there is just the hello, not the X per hello, because I have the $sign there. But because I have the quote, I get an X per of print line hello. So you can say show, and that just shows you what the source code would look like. This print line X per is actually an expression of type unit, but it really represents if someone wrote in the source code print line hello. And so that's how you do, if you make an inline one with this, that's how you do macros now. So anyway, that's my 30 minutes, quick overview. So I can take Q&A. I just want to mention, I did make a discount code for you guys. There's a 5th edition of programming in Scala that does cover Scala 3, not all this advanced stuff yet. We're going to move another volume for that, but there's SBTB pins 5. That's discount code if you want to use that through November 15th. And I'm ready for Q&A.